you can completely replace sodium cyanide with a 100% eco-friendly dressing agent, and you don't even need to change your existing leaching equipment. But before that happens, you have to lock in your parameters. To get those parameters, we use a comprehensive 10-step laboratory testing sequence. This builds a fully validated optimization sheet for your specific ore. Before we start, you'll need your physical prerequisites ready: lab-scale agitators, protective lime, oxidation agents, coconut shell carbon, and precise sieves. Skipping these tests leads to process failure and wasted capital. Executing them meticulously produces the validated parameters required for safe, high-yield gold extraction. Phase 1 is ore preparation. We start with Test 1, the grinding fineness test. This graph plots grind size against the overall leaching rate. We are looking for this exact sweet spot. Increasing fineness exposes more gold, but if you overgrind, you waste energy and dissolve impurities that consume your dressing agent. Once the grind size is set, we move to Test 2, Pretreatment agent selection. Here, we test specific oxidants like lead nitrate or hydrogen peroxide to break down passivation films. As you can see on the right, these agents destroy the rigid shell locking up the gold, accelerating the dissolution rate. Precise ore preparation successfully isolates the gold. This ensures the eco-friendly dressing agent targets only the valuable metal and ignores the surrounding waste rock. That brings us to Phase 2, leaching parameters. We begin right away with Test 3, protective alkali dosage, typically using lime. This dial tracks the pulp's pH. Maintaining this specific alkaline range protects the dressing agent's stability and reduces chemical loss. But watch the dissolution metric. Pushing alkalinity too high constricts the gold dissolution rate, slowing recovery. Next is Test 4, dressing agent dosage. This graph shows agent cost climbing against gold yield. We need to find this exact point of intersection. Adding more agent beyond this limit drives up production costs without yielding any additional gold. Test 5 is leaching time. We determine how many hours are required to reach peak recovery, stopping the extraction precisely when the yield curve flattens out. Leaving the ore in the slurry too long is a trap. Prolonged leaching gives dormant impurities the time to dissolve, accumulate, and physically block gold recovery. Test 6 is slurry concentration, which measures the critical ratio of water to ore. Looking at these two extremes, a thick slurry ruins fluidity and lowers the leaching rate. Conversely, a highly diluted, thin slurry speeds up leaching but wastes reagents and demands larger equipment investments. Balancing pH, agent dosage, time, and concentration establishes the optimal chemical environment required to maximize extraction while keeping your overhead low. Phase 3 shifts our focus to capture. We need to recover the dissolved gold using coconut shell activated carbon. Test 7 is activated carbon pretreatment. We stir the carbon at 1700 RPM, then rigorously wash it through a metallic mesh. This process removes fragile fine-grained carbon. If those fine particles bypass the 16-mesh sieve and enter your agitation tanks, they will absorb your dissolved gold and carry it straight into the leaching residue. To ensure we capture what we leach, we perform Test 8, bottom carbon density. This calculates the precise volume of 6 to 16 mesh carbon required to achieve maximum adsorption rates. We follow up with Test 9, carbon adsorption time, to pinpoint exactly when the carbon becomes fully loaded, which reduces total carbon consumption. Without precise physical carbon management, the gold you just extracted simply funnels back into the waste stream. Finally, we reach Phase 4. Test 10 is the comprehensive conditions parallel test. This is a full-scale lab simulation where we run all 9 of our isolated winning parameters together simultaneously. Implementing parameters piecemeal risks real-time variable conflict. We must ensure these independent chemical streams merge into a single, stable, unified system. Surviving this parallel test is the only way to guarantee stability and repeatability when you transition to a commercial scale. If your parallel test holds up, you have successfully mapped out a validated eco-friendly extraction process. Looking closely at our optimization sheet, you now have a complete roadmap. Every parameter is defined, ensuring maximum economic benefit with zero wasted reagent during full-scale production. Every ore body is unique. If your parallel test results show inconsistencies, you should consult specialized manufacturers like Jinshan for expert guidance on your specific material. Meticulous lab testing provides the physical evidence needed to transition from traditional cyanidation to a predictable, eco-friendly operation.